Hello students, let us discuss positive displacement pumps. The main function of a pump is to move a fluid from lower elevation to higher elevation, from lower pressure to higher pressure, with higher flow rates. Vapor pressure of a liquid is the equilibrium pressure of a vapor above its liquid, that is, the pressure of the vapor resulting from evaporation of a liquid above a sample of liquid. Higher the vapor pressure, the more readily the liquid vaporizes. To keep liquid at the pump from vaporizing, the absolute suction pressure must be higher than the liquid's vapor pressure at that temperature. Pumps may be classified as rotodynamic pumps and positive displacement pumps. Centrifugal pump is an example for rotodynamic pumps. Positive displacement pumps can be further classified as rotary pumps and reciprocating pumps. In the current experiment, only the positive displacement pumps are discussed. A positive displacement pump makes a fluid move by trapping a fixed amount and forcing or displacing that trapped volume into the discharge pipe. Some positive displacement pumps use an expanding cavity on the suction side and a decreasing cavity on the discharge side. Positive displacement pumps can be both rotary and reciprocating type. Gear pump, lobe pump, vane pump, etc. are examples of rotary type positive displacement pumps. Piston pump, plunger pump and diaphragm pump are examples for positive displacement pumps. The gear pump has a drive gear and an idler gear. The shaft drives the drive gear and the drive gear drives the idler gear. In the gear pump, drive is transmitted from prime mover through suitable arrangement to the driver gear. The driven gear, which is in mesh with the driver gear, also rotates. At the suction side, the gears unmesh, allowing the fluid to get trapped between teeth and the casing. At the discharge side, the gears mesh back and forces the liquid out with high pressure. An application for the gear pump is fuel injection in a diesel engine. The driven and driver gears along with the casing are clearly seen. Common gear pump applications include various fuel oils and lube oils, chemical additive and polymer metering, industrial and mobile hydraulic applications, acids and caustic, low volume transfer or application. In a vane pump, vanes slide in and out of a rotor mounted off-center in the casing. Fluid is trapped between two vanes and the casing. Multiple ports permit the pump to operate through a higher pressure difference with less load wear on the bearings. Application areas of vane pump are aerosol and propellants, aviation and auto industry, fuels, lubes, refrigeration coolants and bulk transfer of LPG, ammonia and refrigerants, LPG cylinder filling, solvents and aqueous solutions. In a lobe pump, the rotors are mounted on separate shafts and rotate in opposite directions. The lobe pump operation is similar to gear pump. Instead of the gears, multiple lobes are used. The lobes are fitted with packing strips. Few application areas of a lobe pump are polymers, paper coatings, soaps and surfactants, paints and dyes, rubber and adhesives, pharmaceuticals and food applications. In a reciprocating pump, rotary motion is converted to linear displacement of a piston-like arrangement. In a suction stroke, the piston moves from the top dead center to the bottom dead center. Suction is created inside the cylinder, allowing the fluid to enter. During the discharge stroke, the piston applies pressure on the fluid, forcing the fluid out of the cylinder with high pressure. Main classification of reciprocating pump are piston pump and diaphragm pump. In a piston pump, a piston is fitted inside a cylinder which is designed to push the liquid with high pressure. Piston rings avoid any leakage of fluid towards the crank end of the pump. In a diaphragm pump, a plunger is connected to a sealed diaphragm. With the movement of the plunger, the diaphragm also moves, thereby creating sufficient suction. Fluid leakage from the diaphragm is avoided. Best suitable for corrosive, toxic and flammable fluids. The main application areas of reciprocating pump are oil and gas industries and petrochemical refineries, power plants, water treatment plants, refrigeration and cryogenic applications. At MSR UAS laboratory, a gear pump and a reciprocating pump test rig is installed to analyze the performance of rotary and reciprocating type positive displacement pumps. To analyze the performance of both the pumps, electrical power, shaft power, discharge along with the suction and discharge heads are to be calculated. The hydraulic power output to the pump is then calculated using discharge and total head. The pump efficiency can be calculated as the ratio of hydraulic power output to the shaft power input to the pump. A graph of total head versus discharge and efficiency versus discharge is also plotted. As experiments on centrifugal as well as reciprocating pumps are completed, it is important to know the differences between both the pumps. A centrifugal pump is mainly used for higher discharge, whereas a reciprocating pump is used for high head. In a centrifugal pump, priming is always necessary, but in a reciprocating pump, there is very high suction created at the inlet and hence priming is not required. Discharge in a centrifugal pump is continuous and smooth, but in a reciprocating pump, the discharge is intermittent and fluctuating. Centrifugal pump can handle large quantity of liquid, but reciprocating pump can handle small quantities. Centrifugal pump has less wear and tear and thus less maintenance. However, in a reciprocating pump, there are a lot of moving parts and hence it demands high maintenance. Centrifugal pump can thus run at high speeds, but the reciprocating pump is limited to low speed application. Cost of a centrifugal pump is less when compared to reciprocating pump, which is about 3 times the cost of centrifugal pump for the same power output.
Hello everyone. This is the setup to calculate the efficiency of a gear pump. As we know that gear pump is one of the positive displacement pumps. At MSR UAS, we are having 2 types of positive displacement pump. One of the kind is the gear pump. The setup consists of a storage tank where SAE20W40 engine oil is being stored. From the storage tank, there is a suction line that is fitted along with a suction valve. From the suction line, it enters the gear pump, which is situated over here. From the gear pump, the high pressure fluid is coming out through the discharge line, and from the discharge line, which is having a delivery valve, we can actually control the flow rate of the fluid flowing through the circuit. Further, it flows down to a collecting tank, where by closing the discharge valve, we will be able to calculate the actual discharge of the fluid flowing through the circuit. Further downstream, the fluid flows back into the storage tank, thereby the circuit being closed. The gear pump is being driven by an electrical motor, also connected through a V-belt drive. We are having a stepped cone pulley arrangement, using which we can vary the speeds of the gear pump. On the panel of the gear pump test rig, we have a speed indicator which is shown over here. Also, we can measure the suction pressure that is coming into the gear pump. Here, the reading is in millimeters of mercury. The discharge pressure of the pump is shown on the Bourdon gauge over here. The pressure is in kg per centimeter square. The power consumption for the motor can be calculated using the energy meter. In order to calculate, we have to take down the time required for a certain number of blinks on the energy meter. Now let us go ahead and conduct the experiment. Before starting the experiment, we have to make sure that the suction valve and the delivery valve are completely open. For any type of a positive displacement pump, this should be taken care of. And before starting the pump, now we have to start the mains by switching on the ECB trigger. We will see that the mains indication is glowing on. In order to switch on the panel, we have to rotate the main console switch. Now we can see that the speed indicator is showing 00. From now on, we can start the experiment. To start the experiment, we have to switch on the motor by hitting the green button over here. After starting on the pump, we can see that the values on the suction and the delivery pressure have come up. We can observe a suction pressure of around 260 millimeters of mercury, and on the delivery side, the pressure is above 0.6 kg per centimeter square. The speed of the pump can be indicated over here, which is showing a speed of around 2330 rpm. The power consumption of the motor can be calculated using the energy meter. As we can see, there are a certain amount of blinks. So for that number of blinks, the time required has to be taken, and using that and the energy meter constant, we can calculate the power consumption of the electric motor. In order to calculate the actual discharge of the oil flowing through the circuit, we make use of the collecting tank. Now first, we need to close the butterfly valve. The oil in the collecting tank starts increasing, the level of the oil starts increasing, and we take down the time for a certain amount of rise. After the time is noted, the butterfly valve is opened back again. Now the delivery valve can be closed so that we can have a different delivery pressure of the pump. So by doing so, we can take many number of readings. Once all the readings have been taken, now we can stop the pump and repeat the same procedure for different speeds of the pump. Now the same experiment will be repeated for the different speeds of the gear pump. In order to change the speeds, we will have to shift the belt from this sector to the next section. Now the belt has been shifted to a lower speed for the gear pump. Now let us start the pump and then check for the speed. We can see that the speed has reduced from around 2300 to about 1780 rpm. The same set of procedure will be repeated for this speed and the efficiency of the gear pump can be calculated.
At MSR UAS, we spark your imagination unlike any other.